Hi everybody. Today what we're going to jump into is Trig Equations 2 day. So I'm hoping that everything went well on the previous day and then we got comfortable solving trig equations. Really all we're going to do today is we're going to kind of extend what we dealt with last time. So if you wanted to think of the last trig equations that we solved being very similar to grade 9 equations, that is, we were always able to go through and isolate our trig ratio. That was our primary goal to be able to solve a trig equation. Well, today what we're going to look at is instances where we cannot isolate our trig ratio. And so I want us to kind of think that we're graduating into grade 10 equations, if you want to think of it that way. And you might be able to take a look at the first equation on your screen right now and maybe see why I would say we're now dealing with grade 10 equations. So our strategy as we begin to move is let's make sure that we address everything that we have from the previous day, and today is just an add-on with where we go. So we take a look at that first instruction, and we notice that we've been given a restriction on our angle for x, and we notice that all that states is one positive rotation. So we need to solve for x under those parameters. So the first thing I can look at in my equation then is I have two different trig ratio terms. Now, they are the same trig ratio, but they are two different terms, and I do not have the ability to collect those into one term. And so I'm hoping then that when we cannot collect our variable into one term, we have a strategy, and that is no different to what we're going to talk about today. So I just want to go through a process of which I would hope we would not follow, but it's one that might allow you to see a little easier what we're dealing with. So what I'm going to do is I'm just going to allow some variable that doesn't contain an x because my equation has an x. So I might say like a to equal cos x. And I would hope then that we could look at this first equation as 2a squared plus a minus 1 equals 0. And if we couldn't recognize it earlier, you now see why I said, really, we're dealing with grade 10 equations. You'll notice that we have a quadratic equation in front of us. And so what would we do? We would go through, we would look to factor. And so therefore, we have two numbers that multiply to give 2, two numbers that multiply to give 1, and we need to get in plus 1 in the middle. So if I have a positive 2, negative 1, there we go. And so when we factor that then, you would factor that into 2a minus 1 and a plus 1. Now you get to that instance, that would then allow you to state, therefore a equals 1/2 or a equals negative 1. Now the issue becomes, I never gave you an equation with a's in it. You chose to put in the a's, so now we got to get rid of those a's. So we're going to go backwards then, and let's sub back out that a. So we're going to sub in cos x anywhere that we see an a, and therefore we get cos x equals 1/2 or cos x equals negative 1. I'd like to stop there for a second just to make sure that we can take in everything that we've done, because I also want to make sure that we're good to jump all of that green stuff in the solution. So the first thing, if we pick up from where we left off last time, you'll notice you were unable to isolate your trig ratio in that first term because you couldn't collect your trig ratios into one term. However, we cured the problem down in that final line. That is, you have the ability to then have a trig ratio equal a number, which is what we needed from the last time we solved trig equations. It's still what we need now. Second part is I want us to get back to, let's avoid the green if we can. So what I'm going to do is I'm just going to put a little X through all of that green, because I would hope that we could actually solve this by factoring at the very beginning. Now that we can see that, let's treat the cos x like the variable in this problem, then I'm going to go right back to the very beginning and I'm going to begin my factoring. I need two numbers that multiply to give 2. I need two numbers that multiply to give 1. And I need a positive 1 as my sum. So if I have a positive 2 and a negative 1, I can factor. And so I can then factor that into a binomial times a binomial. My coefficient on the first term is a 2. My coefficient on the first term in the second bracket is a 1, although of course we would never write that. My constant at the end of both terms is a 1 and a 1. Now, what was like the variable in this problem? And we can see it right here, that it's like our variable was cos x. So when I plug my variable into that factor, now I just need to have the proper signs. I've got a -1 in that factor and a +1 in that factor that checks out with my fast factoring chart. And there we go. We get to that point, and I think we should be pretty quick then to be able to state, and even though this line we can skip, that 2 cos x minus 1 equals 0, or cos x plus 1 equals 0, we should be good to come in on that final line then of cos x equals 1/2, or cos x equals -1. Now, we're not done the problem, obviously, because all we've done is solve for what the ratio is equal to. We haven't solved for what x is. But if we get to that point, then what we can do is we can go through and we can create our solutions for each one. Now, all I'm going to do is get rid of all this blue on the bottom, just so we can make a little more room for our solution in red. So, in the first case, my cos x, perhaps I'm still drawing rotation angles. You say cos is positive, so I have to be to the right. And you were then creating your triangles. You never have to show me the blue. Please feel free that if you can start to have a picture of that in your head and say that if my adjacent side is 1 and my hypotenuse is 2, then I know I have a big angle in there. What I'm talking about then is a pi/3 related acute angle. And in the first quadrant, I would get pi/3, and in the last quadrant, I would get 5 pi/3. For the next equation, because it's a cos value equal to -1, and I know that cos equaling -1 is a minimum value on my cos graph, then maybe I'm just thinking about that minimum value then, and where it occurs, and I know that that occurs at a value of pi. So I'm just going to box in right now that if you gave me this red solution, then that is all I would need to see. That's it. You wouldn't have to show me any of the green, and you definitely wouldn't have to use the substitution earlier on to be able to solve. So maybe now you can see why I really call this a grade 10 problem. We can learn how to solve some equations that happen to contain some trig ratios by using factoring. Okay, we're going to pick up the pace and we're going to move a little quicker as we go. So what I want you to do, just take a look at the equation you have in B. And the first thing that I want us to do is to pause it, give it a shot. It's going to be something that you haven't tackled before, but I do think that we have in our background enough to be able to solve it. So pause it now if you want to give it a try. Otherwise, I want you to take a look at this equation because there is a very common mistake that we make in this equation. That is, we get so focused on the squared that we start to think about, hey, this is a quadratic equation just like A, and so I'm going to try to factor that thing, and so I'm going to bring everything over to that same side as the squared sign, so I now have a plus of that, and I have a -9 equals to 0. And now I go through and I try to factor that. So I got like my 2 and 2 and a 3 and a 3 and so on. And I just want to stop for a second. Because maybe and hopefully you noticed my key mistake. That when you look back up into that equation, you have two different trig ratios. And so for us to be able to go through and factor this somehow, I'm going to need coses in my first term. Yes, I'll have constants in the end, but there's no way when I expand those that they're going to give me sines. So let's make sure that now that we can address quadratic trigonometric equations that we don't all of a sudden make the focus be the quadratic portion. Your focus in this equation should be, and I'm just going to erase this whole part top, it should be the fact that you have different trig ratios at the beginning. So we should be able to move pretty quickly in this because you know that you could write those with the same trig ratio by replacing your cosquared with 1 minus sine squared. Now everything is going to be in terms of sines, so after we go through and we simplify that to individual terms, now we're going to think about everything being on the left side of that equal sign so that my squared term happens to be positive. And we come in on that line. So you'll now notice that that red line looks an awful lot like problem A. We have the means to be able to go through and solve. So pretty quickly, we're taking a look to see if we can factor. And yes, we can factor because a -2 and a -10 does give me -12. And so when I go through then and factor that, I'm going to get 2 sine x minus 5 times 2 sine x minus 1. And notice I can skip over my substitution and I can go straight to a factored form. Once I get to that point, I can then solve that sine x is going to have to give me 5/2, or sine x is going to have to give me 1/2. So, a couple things right off the bat. We get down to that point, we're doing great, and you are kind of proving to yourself you're pretty good with all that algebra. The next part becomes actually solving the equation. We haven't solved it because we still don't know what x is. So, take a look at that first possible solution, and I forgot my therefores out in front there. But when we take a look at that first possible solution, you recognize that 5/2 is not a special angle, and therefore you go through and you say, oh, I need to use my calculator, and you go through to solve. I would like to draw your attention to something that you should have addressed way back in grade 10, probably hit out last year a little bit, and this year we should definitely have down. I want you to notice that if I broke that down fundamentally to what sine was, that's going to say that this is my opposite side and this is my hypotenuse. And so we should already have a problem then with what's on your screen. That there's no way that my opposite side can be longer than my hypotenuse. So for the calculator junkie who's going through to try to calculate maybe alpha, the related acute angle, and you're therefore doing the inverse sine of 5/2, and you then see error on your calculator screen, we now can see why. On a greater understanding level, remember that when you graph your sine curve, the maximum value of your sine curve is at 1. The minimum value of your sine curve is at -1. And so anytime you happen to have a sine value that is outside those ones, that is, if I don't care about the sign of it, but I just look at the number, any ratio value that's going to be greater than 1, I cannot accept. So when we get down to that point, we should be good that sine x equals 5/2 is a solution that works for that equation. However, we can't accept it in the problem. And so therefore, we're going to mark that as inadmissible. And then we can jump in and we can work through on our sine. So we may be, and hopefully you're getting to the point where we don't even have to draw rotation angles. That we can look at that blue solution of sine x equals 1/2, and we can say to ourselves, sine's positive, so we know we're up. We're quadrant 1 or quadrant 2. Sine is opposite, so my opposite is 1. That's going to mean I have a small angle, and therefore x is going to be π/6 in the first quadrant or 5 π/6 in the second. There we go. So what you see in B then is a combination, what we dealt with in A, but maybe we have to use some identities from our past to be able to go through and solve that equation. Okay, let's keep it moving. So what I would like right now is everybody to pause the video, give this one a shot, please. Okay, we're back. And so our first look was, do I have the same trig ratio? The answer was yes. And so since it's already written in standard form and you can't collect your sine x's into one term, we're going to look to factor. Two numbers are multiplied to give 4, two numbers are multiplied to give 3, and that's going to give me my middle term of 4. And so if I factor that into a 2 sine x plus 3 times a 2 sine x minus 1, then we come in on that level. We should be then good to state that sine x is going to give us negative 3/2 from the first factor, or sine x is going to give me 1/2 from the second factor. Okay, now that we're able to solve, we're pretty good to state that this first factor is going to be inadmissible in terms of solving. Now, I want to extend our language a little bit. And this is where we get a little dicey in terms of communication. That technically, this would not be inadmissible. The answer to this question would be no solution, because I can't solve that equation. Like, there's actually no solution to it. That's why the error kicks out on your screen. Opposite side cannot be longer than hypotenuse. However, if we were able to solve it, and it would then give us a value we couldn't accept, that would be deemed inadmissible. So, a couple things. We're not going to be that concerned about language this time. Okay, you take a look then on that second one, sine x equals 1/2, and we should be good to say sine is positive, so we're up, small side, small angle, and therefore x is going to give me pi by 6 in the first quadrant, 5 pi by 6 in the second. There we go. Hopefully a little confirmation, and we're feeling a lot better about working through. Okay, so let's take a look at D, because I want us to make sure that we're good, that I would argue to you D should actually be a pretty straightforward problem for us, but I'm going to bet and say that a number of us are going to hit a snag on it. So let's pause the video. Let's give this one a shot. Okay, we should be back. So a couple things to maybe focus in on. The first thing that we should recognize is you have different trig ratios. Our issue becomes that we don't have a nice, neat identity to be able to replace a sine in terms of cos or a cos in terms of sine. Don't get confused between sine squared equaling 1 minus cos squared versus cos squared equals 1 minus sine squared. Notice neither of those ratios are squared in our equation. Okay, so how can we work our way through then to be able to solve? Well, the next mistake or issue that we could come across would be that we look at it and we say that, hey, I've got a sine x on both sides of my equal sign. And so why don't I just divide out a sine x from both sides? I'll get down to a cos x equaling 1, and I'll be good. I want to make sure that we never, ever, ever make that mistake. Because what you'll notice is you just divided out a variable from both sides of your equation. If there's anybody who has an issue with that and says like, yeah, but what's wrong with that? I'm just going to give you a pretty direct equation. If I gave you x squared equals 3x, and you said, yeah, well, I have x's on both sides, so I'll divide out an x from both sides. I get x equals 3. Well, I hope that we can see that we're also missing a solution. That yes, 3 makes the left side equal right side, but clearly x equaling 0 would also make the left side equal the right side. And so the act of us dividing out the variable means we are going to divide out a solution. And so we should never, ever, ever divide out a variable from both sides of an equation. And so if we do get into that instance, then, okay, what do we do to be able to solve? I hope that you guys can see that this is actually a pretty straightforward grade 10 equation. that if we were to take a look at an equation like x squared equals 3x, I would hope that we would say, can you put your x's into one variable term? No. So then move everything to one side and set it equal to 0. And so we can do that same thing here. That is, we can get rid of that sine x on the right side by subtracting a sine x. And now when we take a look at our equation, we notice that our preference should be to be able to factor whenever possible. And so therefore, we can factor that blue line by saying that I have a sine x in both of those terms. And so I'm going to common factor out a sine x. And now I'm factored. As soon as I'm factored and I have it equal to 0, then I know one of those factors has to equal 0. So therefore, the first factor equals 0, or the second factor equals 0. Now that we got down to that point, we have our trig ratio isolated. Now we can actually solve for our variable. Now, when you take a look at the value that sine is and the value that cos is, we should notice that those are key values on our sine and our cos curve. I'm just going to picture my curve to get my solution. And so if I think about my curve for my sine curve, I know my sine curve hits 0, at pi, and at 2 pi. And I know that my cos curve hits 1 at 0 and at 2 pi. Now, when you take a look at that yellow line, you're going to notice we've duplicated solutions. Don't ever, ever, ever do that. When you solve an equation, you don't repeat it. If a solution exists to an equation, then it's stated, no matter how many times it's the solution. So therefore, your final answer would actually be 0, pi, or 2 pi. And you would never need to show me that line. Okay, there we go. So not too bad. Common factoring can also be a strategy for us to be able to solve trig equations. Okay, now we're going to jump into some different sort of stuff. I'd like you to take a look at the equation on the screen right now. And maybe you can see what's different about this equation than every equation previous. If we can't, then I'm going to add in what would have been in problem 1. That's the way that equation would have looked if we had tackled that earlier today or our last lesson. So I want you to notice that restriction of one positive rotation has been removed. That means that when we solve for x in this case, we need to solve for every possible value for x, not just on the first positive rotation. Okay, what I would like everyone to do is to pause the video now and go through and solve this equation as if this was a part of question 1. Go to it. Okay, we should be back. And so if we go through and we look to factor 3 and 1 on my factors of 3, factors of 2, 2 and 1, I need a negative 1 in the middle. And so therefore I can factor that into a 3 sine x plus 2 and a 1 sine x minus 1. Now that we get to that point, you have the ability to solve for your trig ratio, that it's equal to negative 2/3, or sine x is equal to 1. Okay, and now we can go through and we can solve for either one of those. Oops. Well, in the first equation, I notice sine x equals negative 2/3. That is not a special triangle. So I'm going to have to go and do my inverse sine of 2/3. Remember that I am not taking the inverse sine of negative 2/3. My suggestion to you is, if it is not a special triangle, draw a picture. Because now when I deal with my inverse sine, I'm going to find that related acute angle is approximately equal to 0.73 rads. And so if you were to go through and you were to solve this problem, we would then go through it and state, okay, so therefore x could be pi plus 0.73 to get into the third quadrant, or 2 pi minus 0.73 to get into the fourth quadrant. On the last equation, in blue, sine x equals 1, we should all be good that you know that your sine curve hits a max of 1 at exactly pi by 2. Okay, if you have that as your solution, you are doing great. That would be us solving any trig equation if our restriction was one positive rotation. However, we've removed that, which means we now need to create a statement that represents all possible solutions. And I'm hoping that maybe just even me saying that is going to bring about for you, we're going to go back and we're going to write some general statements. So this is what we dealt with kind of at the beginning of the unit, of us going through and being able to make a statement that represents all possible values. So let's take a look at this first one, and I'm just going to put little number 1 beside it so we can see where everything comes from. That would be us rotating into the third quadrant. Well, you can get to that third quadrant by taking pi and adding to that 0.73. And so if you take your pi and your 0.73, you would get to an x value of approximately 3.87 rads. Now, how can we get into the third quadrant? Well, we can get to the third quadrant by rotating 3.87 rads, and then by rotating a full rotation in any direction from there. So how do I write plus a full rotation in any direction? And there's my plus 2k pi. And I'm hoping that maybe as you take a look at that, you go, there's our general statements from earlier on. Okay, all I'm going to do is I'm just going to get rid of a little of that so we can get rid of all those arrows on that diagram. Went a little too far. And there we go. Okay, well, we could have also got to the fourth quadrant. And so if you take a look at the fourth quadrant, I'm just going to put a little number 2, is that would have been rotating 2 pi minus your 0.73. So we should be good. Oops, I forgot to add on my 2k pi here. So we should be good to state that x could approximately equal 5.55 rads. And that would be us rotating into the fourth quadrant. I don't think you need me to draw on those arrows anymore, but we could get to that fourth quadrant of 5.55 rads and then rotate any number of full rotations in either direction, so therefore we could add on a 2k pi. Don't forget about that last solution. We would have our third solution to that equation in that we could exactly equal pi by 2. Notice no approximate symbol. But then go any full rotation in either direction and also get to that value of 1. So when you take a peek back on it, you actually have 3 solutions to that whole equation. And there is how we go through and we solve trig equations when there is no restriction on your variable. Okay, let's try another. Okay, so we take a peek at B, and here's where I would say normally we would go through and we would work on this. And I would let you guys go a little bit, and I would even crack a joke, a horrible joke, about how much you would really wished that minus at the end on the 4 was really a positive, because then you could have factored that equation. And instead what you take a look at is that equation does not factor. And so I would come back to you and I would say, well, what would you do if you had a quadratic equation that didn't factor? And we should be good that we would be using quadratic formula. Well, that doesn't change here. Now, I'm going to write something down that's incorrect, but I want to show you why, because it is the most costly mistake you can make when solving a trig equation. Here we go. So, therefore, x equals, and I have my negative b plus or minus the square root of b squared minus 4ac all over 2a. And we would go through and we would even clean that up a little bit. And you would get down to that point. Now, I would like you to all see that that is incorrect on the page. I've made an error and a big error. And for most of us, we're probably looking in the wrong spot if we can't see it. Keep in mind what your variable is here. Like when we went back and we used substitution to be able to solve this, you would have allowed cos x to be equal to another variable like a. And so if you viewed this as a squared minus 5a minus 4 equals 0, you wouldn't tell me, therefore x equals blah, 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 blah. You would have told me, therefore a equals. I want you to notice that my mistake was over here, but it is a really costly mistake. That when I use quadratic formula to be able to solve this problem, there's nothing wrong with me using quadratic formula. In fact, I need it in this instance. I just have to remember that I am solving for the value of cos x, not x. So, therefore, cos x could have those possible values. Okay, now I'm going to work my way through. So we get down to this point and we say cos x is equal to 5 plus or minus root. So I can already see, and all I'm going to do is just write out a decimal approximate. I would not use this because this is not going to be exact enough, but I'm going to write a decimal approximate beside. I find that the positive case is about 5.70. Not that we needed our calculator to be able to tackle that. You take a look at what root 41 is, and we should be good that that's 6 point something. So 5 point something plus 6, or sorry, 5 plus 6 and a bit is 11 and a bit, and 11 and a bit divided by 2 would be 5 and a bit. If we deal with the negative case, we would have 5 minus root 41 over 2, and that's going to get us approximately to negative 0.7. Okay, I'm hoping, given our discussion from prior, that you know that cos x cannot equal 5.7 because the maximum value of cos is 1. And so this positive is actually inadmissible. It does not yield a result. I want to notice that I didn't mark that as no solution. It's that I can't accept that positive. Now I take a look at the other. I can accept the negative. I am totally fine, and I actually like it that my cos x is equal to negative 0.7. So I can accept the negative case. However, I have to be very, very careful. If I worked my way through and I dealt with cos x equaling negative 0.70156, blah, 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 and now I immediately go inverse cos of that value, I'm going to come up with an x value that's going to get me about 2.35 rads. And for a lot of us, we might be okay with that. But I'm hoping that you can see that when you solve for that, you maybe didn't solve for what you thought you were. I'm going to continue on in the gold, and maybe we can see our mistake. You would have said cos is negative, and therefore we are left. You would have then went inverse cos on your calculator, and you would have gotten a related acute angle of 2.34 rads. Maybe you can see the mistake on the page right now. I'm going to go back and just put in some good old decimal approximates. You know that if you rotate to your negative x-axis, that's a pi, rotation, so it's about 3.14. And if you take 3.14 and you divide it by 2, remember, pi by 2 is about 1.57 rads. Then how is your related acute angle 2.34? We found an incorrect related acute angle. So why did we find that? It's because we did the inverse cos of a negative value. So what I'm going to write down is to get rid of all of this mess, and I want to go through an approach for you that can help you out an awful lot. Okay, the first part is we recognize, circled in gold, that we can accept the negative value. So on our calculator, we are going to push buttons, and we are going to push 5 plus root 41 divided by, 5 minus root 41, the solution we can accept, divided by 2. And on our calculator screen, we are going to leave that big, ugly decimal. However, what you'll notice that I circled in blue is that we see that it is negative on our screen. So right away then, deal with the fact that you know where cos is negative. Left. Now our problem becomes we need to change the value of that big ugly decimal you have on your screen from a negative to a positive. So let's just multiply it by -1. Now you have as exact of an approximate as you can have in your calculator. Now let's go inverse cos of that value to figure out the size of your related acute angle. And you should get about 0.79. That keying sequence is going to be the best way for you to be able to get an exact or as exact of an answer as you can. Now we can finish off the problem. And we can come in and we can then say, well, therefore, x is going to put us in the second quadrant, so pi minus 0.79. Or it's going to put us in the third quadrant, pi plus 0.79. So x is going to give us approximately, and if I take my pi and I subtract my 0.79, you'll notice that I actually get the value that I mistakenly got before. Then I go through and I get my 3.14 and I add on my 0.79 and I get 3.93. Now, the one key thing that we didn't forget about, I know we didn't, was that we didn't have a restriction on this, which means we need to include general statements. And so I need to then say, or any full rotation in either direction. Same thing here. And now we have a great solution to that. Okay, some of us may have forgot because it has been a while. But just remember that when you do the inverse cos of a negative value, your calculator is programmed with rules. And that calculator is going to say, if it can give an answer to this question that we're going to call happy face, and happy face exists in the first quadrant, then it's going to give you the first quadrant solution. If it can't give you that, then it's going to give you the second quadrant solution. And that's what you just experienced there. Your calculator could give you the first positive angle that exists for a negative cos value. It actually gave you the principal angle when you pushed buttons on your calculator. I think the keying sequence that we just went through on B, which allows us to be exact as we can be and treat solving all of our problems the same, is going to help us out moving forward. Okay, a couple more. Okay, so let's take a look at C. I think we should be okay on C to tackle this one and move forward as we go. So let's pause the video now and finish it off. Okay, we're back. So first thing I notice, I have different trig ratios. I have tan x and cos x. So what I'm going to do, what I'm going to do is I'm going to get everything to one side. I don't think I want to sub in sine over cos for my tan because I don't need to. You'll notice that my blue would allow me to now common factor out a tan x and get to that point. Now that I'm at that point, I can actually solve it by saying I need when is the first factor equal to 0 or my second factor equal to 0. I really hope that we're good on this. However, I understand that not everybody's going to come to that as quickly. I'm going to put the whole thing down as we go. That cos squared x minus 1 would equal 0. So cos squared x equals 1. And now to get rid of that squared means I have to take the square root. Square root of 1 is 1, but every time I take the square root, I have a positive or a negative answer. So I never need to see that red. You feel free to just come straight in and state that cos x equals plus or minus 1. Now, think about yourself, though, that if you think, oh, that's going to be where I make a mistake, then my suggestion to you would be factor it fully. Now, this is going to force you to write down a negative 1 from the first solution and a positive 1 from the first factor and a positive 1 from the second factor. Okay, we're coming in on those red values. We should be good to solve that. I know it's our tan curve. It's the one we're probably least comfortable with, but maybe we remember that our tan curve looks something like this with that good old wavy thing. And so my values for 0 on my tan curve would be at 0, pi, 2 pi, so on and so on and so on. On my cos graph, that's just saying when is my cos curve at 1 or negative 1? And I would be coming in on a 0, pi, 2 pi, that I actually get duplicate solutions for the whole thing. So we should be good then to be able to finish that whole thing off. And I know that everyone is going to write down as their final answer. I'm going to bet and say I got a few of you on with that. Remember the first part, we need general statements. There is no restriction on your variable. However, we're not going to write, therefore, x equals 0 plus k pi, because that's how often it repeats every pi units. We also look at our cos curve and notice that an acceptable value repeats every pi units. And so we can shorten that whole thing up by just having k pi. There we go. Nice. One more to go. Okay, we take a look at this last one, we should be good. The reason why I wanted to talk about the last one is because something very important can happen on this last one. And I would throw this last one into a problem-solving category. That when you start to tackle something in this, there was actually something in the last problem that we left out. And it was actually an issue with the last problem. Not that the solution was incorrect, but it was something that we omitted talking about, and we'll see it in play here. I'm going to go very quickly because I'm going to assume that everyone is very comfortable in solving this problem. So, we should be okay to bring that cos x and have everything be on the one side. You have two terms that have a common factor. Let's factor it out. That allows you to state that cos x equals 0 or tan x equals 1. Well, now you could work your way through and you could solve. And you would say, when is your cos equal to 0? Well, that's at pi by 2 or 3 pi by 2. And then when is your tan equal to 1? Well, maybe we can picture our tan curve well enough. Maybe we're going to rotation angles and you're saying when are your opposite and adjacent sides, same sides? Not sure. But you would then state that it would be pi by 4 as an angle in the first quadrant, or 5 pi by 4 in the third quadrant. Okay, we get down to that point, and as I said earlier, if you're able to give me that solution, you're doing great with trig equations. However, there is a big concept that we've missed. Remember that when we solve an equation, we're actually solving for values of the variable that make the left side equal to the right side, that make the statement true. And so I just want you to notice, like if I went and took pi by 4 and I subbed it back into my equation, then my left side is going to be the tan of pi by 4 times the cos of pi by 4, and my right side is going to be the cos of pi by 4. Well, when we calculate, what's the tan of pi by 4? Well, it's 1. Then after all your identity work, you notice that the left side is pi by 4, the right side's pi by 4, you're good. We didn't even have to get to the point where we actually replaced the cos of pi by 4 with 1 over root 2. So we get confirmation that that works. Well now, what if I took pi by 2 and I subbed it back in? I calculate tan of pi by 2 on my left side times the cos of pi by 2, and my right side is the cos of pi by 2. And so the cos of pi by 2 on the right side is 0. I like that. The tan of pi by 2, oh, wait a second. I'm going to go up to the top right corner and just put on that tan curve again. And I don't even need any more of that curve. But I will put it on just so we can see that at pi by 2 and 3 pi by 2, remember, your tan value is undefined. Now, for anybody who then looks at that and goes, well, that's no problem because the tan of pi by 2 is undefined, but undefined times 0 would still be 0 because anything times 0 is 0, and I got to say, stop, no. Because you have the tan of pi by 2 being undefined, left side does not equal right side. And we hit a big snag in this situation. So maybe you can see why this is a problem-solving question, and I'm just getting rid of all of this stuff on the bottom so that we can adjust our actual solution. Okay, how could I tell at the very beginning that this was going to be a problem so that I don't have to go through and always check every solution back with the original? I'm going to just write up in this beginning something from your grade 11 year, and the fact that your tan is equal to sine x over cos x. I want you to notice that tan equaling sine over cos actually puts a hidden restriction in the problem. That because tan equals sine over cos, and cos x is on the denominator, then that means that cos x can never equal 0, because then I would have an undefined value. Okay, so you can see it in two instances. Yes, we can't accept it because at pi by 2, your tan is at an asymptote, so undefined. But also at the very beginning of the problem, I could see that if I were ever to get a cos x equals 0 solution, that I could not accept it because of that restriction. And so I didn't even have to find pi by 2 or 3 pi by 2. As soon as I said that I had an equation that said cos x equals 0, I can mark that right away as inadmissible. I don't have to state why, but it's because cos x cannot equal 0. And so therefore, the only solutions I can get then come from that second equation, and I'm just going to highlight those in green. So how do I now make sure that I write my final solution in good form? Well, I can pick either one. I'm talking about x, pi by 4 or 5 pi by 4. And you notice that those two terminal arms are always pi units apart. And so if I add on a k pi, I can rotate in either direction and make sure I lie in that same position. Okay, I would call D your doozy. That one's got a little something extra to it. Okay, if you were able to work your way through today, you are doing outstanding. Jump in and get some practice. We're almost there. Good luck.